This is the Chapter 2 review. The first problem is justifying each step with a property of equality. We learn these properties of equality starting on page 28 of the text. There's two halves of this actually. If you recall on the page 33 in the order of operations horseshoe, it says to do anything you can in the order, please excuse my dear Aunt Sally, to simplify an expression looking for distributive property when you multiply and divide, and looking for combining like terms when you add or subtract. What I've got outlined in blue is simplifying the expression down into its simplest form. That's actually the first part of the order of operations horseshoe, and then after that we're going to take what we have there and we're going to solve by undoing. And so the blue part is going to be doing in the order, please excuse my dear Aunt Sally, to simplify. And the green is going to be solving by doing, solving by undoing in the reverse order of operations using inverse properties. When we're simplifying, we're going to be using things like commutative, associative, distributive, and substitution. Not necessarily in that order, but that's what we'll be using. When we start undoing, we undo subtraction by the addition property of equality. We undo addition by the subtraction property of equality. We undo multiplication by the division property of equality. We undo division by the multiplication property of equality. And we use reflexive property to show our work. So there's your options in the two categories. Now all the way down we're using the order of operations to try to solve. So here's what we would do. We would look at this and say, okay, I've got multiplication, addition, parenthesis, subtraction. I want to do anything I can in the order, please excuse my dear Aunt Sally, to simplify. Now what we would do first is what's in the parenthesis. I can't do what's in the parenthesis because they're not like terms. I cannot do the multiplication, I cannot do the addition, and I cannot do the subtraction, so I can't do anything. I can't do anything because my like terms are not together. If I could get my like terms together, I could combine like terms. So what I'm going to try to do is to rearrange things and regroup things so that my like terms are grouped. In my parenthesis, my grouping symbol, I have unlike terms. Now, if I took that parenthesis and I shifted it over to there, it still wouldn't help because I would still have unlike terms. Or if I took that parenthesis and shifted it to here, it still wouldn't help because it still wouldn't have like terms together. I want to shift my parenthesis onto like terms, but there's no way to make that happen because my like terms are not beside each other so that a shift will do any good. So the first thing I need to do is to change the order of these numbers that are being added so that my like terms are beside each other, making a shift of the parenthesis something that would be good for us. Now, when we're justifying statements with a property of equality, we want to know Where did this come from? What is this a result of? And the first statement was not a result of anything, it was given. So in an algebraic proof, we make the first statement given. Now, we want to know what property lets us do the move that we're trying to get done. We're trying to change the order of addition. Rearranging or changing the order of addition is commutative property. And so this is a result of the commutative. We change the order of the 7 and the 2x. Now, I still cannot do what's in the parenthesis because I still do not have like terms, but I have got my like terms beside each other so that a parenthesis shift would do some good. If I shifted my parenthesis to the left, I would get this. I could also insert parentheses on the right. The property that allows me to shift my parenthesis or to regroup is called the associative property. By using the commutative and associative properties of equality, I now have my like terms grouped together in a grouping symbol, so that when I ask, can I now do what's in parentheses, the answer is yes. We can do what's in the parentheses because we have like terms. Now I'm actually going to do negative 3x plus 2x and replace it with its answer 1x. I'm going to do 7 minus 9 and replace it with its answer negative 2. In a basketball game, when you take one player out and replace that player with another one, we call that a substitution. That's what we call it in mathematics also. If we take this and replace it with what it's equal to, negative 1, then we substituted the negative 1x in its place. If we take what this is equal to, 7 minus 9, and replace it with negative 2, then we've made a substitution. So we used commutative, associative, and substitution properties of equality to simplify the expression by finally doing what was in the parenthesis. Now, there's nothing else that we can do to simplify this expression. Negative 1x minus 2 is as simple as we can get. The second thing on the order of operations horseshoe is to get the variable we're isolating on one side of the equal sign, remembering to change the sign when we cross over, but there's not x's on both sides, so that doesn't apply. So we go to the third piece of the order of operations horseshoe, which is to undo. Our operations are multiplication and subtraction. We undo subtraction by addition. When you undo subtraction with addition, you're using the addition property of equality. This is the result of the addition. And so I put addition way down there. Notice I skipped one. The addition property of equality says that we have to add something of equal value to both sides. That's on page 29A of your student edition. The property says that something is equal to itself on page 28 is reflexive property. Notice that we're using reflexive property to show our undoing process. Now, we have the operation where at this point we've given the reason we got there, and now we need to make our next move. We're going to undo multiplication And what undoes multiplication? Division. So we're going to divide both sides by negative 1. So we have 18 divided negative 1 is negative 18. When you undo multiplication by division, you're using the division property of equality. The result of that division is here. Notice we skipped a line when we put division property of equality. In showing our work again, we needed to make a statement that said what we were dividing each side by was equal to itself, and the property says that something equal to itself is reflexive again. So the first part of my proof, I was using commutative, associative, distributive substitution. Those were my choices of things that I could do to simplify the expression, or to get the expression to the point I could simplify it by combining the like terms in the parentheses. After that, we were undoing, and when we're undoing, we're using inverse operations, and the inverse operations are on page 29A of your student edition: addition, subtraction, multiplication, and division properties of equality. In showing our work, we needed to make a statement that what we were adding to both sides, or what we were dividing both sides by, was equal to itself, and that property that says that is reflexive. At the end of this, we have these two statements. Negative 18 equal x, and x is equal to negative 18. What's going on here is that we don't necessarily like it to say number equal variable. We'd prefer that it says variable equal number. X equal negative 18. The property that says that you can flip the equation around is the symmetric property of equality. Be very careful not to confuse symmetric with commutative. On commutative, we change the order of addition. On symmetric, we flip the equation around. On commutative, there's either a plus or a times sign there. In symmetric, there's an equal sign there. Well, I hope that explains to you, helps you understand page 46, question 1. It is your job to know, memorize, and understand these properties, so you need to commit them to memory by studying your page 28 through 29A. And then hopefully this will help you understand how to use them once you've committed them to memory. All right. Numbers 2, 3, and 4. Number 2, it says distribute. Since it says distribute, then we need to see parentheses, because distributive property looks like this on page 31 of your student edition. A times B plus C, and we're distributing through there. So we want to rewrite the 4 1/2 as 4 plus 1/2 and distribute the 8 through the parentheses. So we're going to take 8 times the first thing 4 and 8 times the second thing 1/2. So we have 8 times the first thing 4, 8 again times the second thing 1/2. We have to write the 8 over 1 for the half because the half is a fraction. On the 8 and the 4, you don't have to write them as fractions. You can just write them as whole numbers. We do 8 times 4, which is 32. 1/2 times 8. You cross-reduce to a 4, so we get a 4. This yields a positive answer, and so we put a plus to separate our terms, and then 32 plus 4 is 36. distributive property. Same thing here. We have 6 times parenthesis. We're going to distribute the 6 through the parenthesis. So we have 6 times the first member x, 6 again, times the second member 8. And so we go 6 times x is 6x, 6 times 8 is 48. Notice that I don't put the plus or minus right there. I wait until I get a sign rule answer for the second half. The sign rule answer, positive 6 times positive 8 is positive 48, and because that's a positive, I put a plus back. You cannot add those because they're not like terms, and so it simplifies to 6x plus 48. Number 4 is the same thing. It's asking us to distribute. So we're going to take what's outside the parenthesis and multiply it through the parenthesis to the things on the inside. I'm going to make myself a little more room here. So we're going to take the thing outside, negative 4xy square, square root of 3, times the first little piece inside, 2x square, square root of 2. And then the thing outside again, negative 4xy square, square root of 3, times the second thing outside. Now when we take that second thing outside, remember from page 18 and following that we carry the plus or minus as a sign, and we call that a negative 5xz. Also recall that I don't take that sign down here. I take the sign over there, and I use the sign rule answer for this to tell me what to put in there. So when you multiply the numbers. 4 times 2 is 8. When you multiply with different signs, the answer is negative, so negative 8. And then you multiply the names. We do x's with x's. When you multiply with like bases, you add the exponents. So x to the first times x to the second is x to the third. And then we do our y's with our y's. Y to the second, and there's not a partner for the y, so we bring the y squared down. And then you do the radical. Square root of 3 times square root of 2 is square root of 6. You multiply them. And then we go to the second half. We multiply the numbers. 4 times 5 is 20. The sign of the 4 is negative. The sign of the 5 is negative because we carried the minus as a sign. When you multiply with the same sign, the answer is positive, so we put a plus back, even though it was a minus to start with. What we put back was not what was there. It was the sign rule answer to this. The sign rule answer was positive, so we put a plus back. Then we do our x's with x's. We multiply the names. When you multiply with like bases, you add the exponents. X to the first times x to the first is x to the second. Y to the second. Y didn't have a partner, so we cram it on. Z to the first understood. Z didn't have a partner, so we cram it on. The radical square root of 3 didn't have a partner, so we cram it on. My operation now is addition. You cannot add those two because they're not like terms. So that's it. We simplified the expression by combining like terms.